All right. We're going to look at section 9.1, scatter diagrams and linear correlation. We're going to start looking at how two different variables relate to one another, or if there is any relationship between the two. So are they correlated? Now, correlated just means they're acting in some kind of possibly related fashion to each other. But we're not going to make any claim about causation or not. So if we have a positive correlation, that means when one goes up, the other one also goes up. If one goes down, the other one also goes down. A negative correlation indicates they work in opposite directions. As one goes up, the other one goes down. As one goes down, the other one goes up. And so different things will act in different fashions with each other, or they'll both be influenced by something else that's causing it. So we're gonna look at making scatter diagrams of data pairs. These are XY pairs, data points, basically. X, we're going to call the explanatory variable. So when you graph it, your explanatory variable is going to go on your x-axis or your horizontal axis. Y is called the response variable. That's going to go on the y-axis. The response variable is going to go on the y-axis or the vertical axis. Another way to say that. And then just because we have a correlation does not automatically imply causation. So kind of the example I use was I got a new car a couple years back, and one of the features this new car had is it kind of said something about if your tire pressure got low, it would give you a little alert. And I noticed every time I would turn the heater on that my tire pressure also got low. So therefore my heater was causing my tires to go low. No. What was happening was the temperature outside was getting really cold. That's why I turned my heater on. And then my tires were also losing pressure because of the cold temperature. It was reducing the pressure in the tires. So the tire pressure and my heater use was both being influenced by the outside temperature. So that's what we mean by, two things might be acting in a similar fashion or inverse fashion to each other, but it may be because they're both being influenced by something else outside of that. So we got to look outside of that relationship. All right, here are some types of correlation. So as for a negative linear correlation, as x increases, as you move across to the right, y decreases. If you remember your algebra, that means you have a negative slope if you were looking at a line. So you have a negative slope, negative linear correlation. As x increases, y increases, that would be a situation of a positive linear correlation, okay? And then down here on the lower left-hand side, the data is just kind of all bounced around. There isn't really a pattern to it. And so we'd say there's no correlation there. In this bottom right-hand side, we can see it's kind of making it almost a parabolic shape, maybe an absolute value. Who knows? But it's definitely not linear. It's definitely not a linear shape. So that's a non-linear correlation situation. So, maybe if we're only looking at this is the danger of looking at data, right? If we only had looked at data from the lower half, we might have thought it was positive. Or if we just looked at data from the upper half, we might have thought it was a negative linear. But since we have all that data, we see a non-linear relationship. So we do need to be careful about making any claims too strongly one way or the other. A numeric measurement of how closely a data set matches a linear model is given by what we call the correlation coefficient. It's going to give us some kind of measure about how closely we think this data is linear. And it's also going to give us an indication of whether we think it's a positive linear or a negative linear. So we're going to call this R. R is going to be our sample correlation coefficient. Rho, so it looks like a P, but it's called rho. It's Greek letter rho. And that's going to be the population correlation coefficient. So how strong are these things related in the population versus how strong are they related in our sample? And today we're going to worry about the sample one, the R, but you should know rho as well, as that's the one for the population. And this value is going to go between -1 and 1, -1 and 1. So some comparisons here. If we have the first two are positive rho or R values, correlation coefficient values, and we can see for a level of 0.7. Now, there's some subjectivity about this. I think this book kind of decides 0.7 is kind of like on the border of whether it's a high or low, or sorry, high or moderate. And just for the class, I'm not claiming this is absolute. Again, different books are going to say different things, but we're just going to say if this R value is greater than or equal to 0.7, we're going to call that a high or strong relationship if it's 0.7 or bigger. If it's between bigger than 0.3 or equal to, but smaller than 0.7, we're going to say that's a moderate linear relationship. And then anything less than 0.3 absolute value, we're going to say this is a low or weak linear relationship. 0 is no relationship. So this is no relationship. So you can see at this 0.7, and again, 0.7 is a border. Some books might call that moderate. Some books might call it strong. It's right at that border about where most books kind of make their decision. Same thing with 0.3. 0.3 is right at the border. Is this a strong or is it a moderate relationship? And you just kind of, like I said, just for this course, we're going to say 0.7 or higher is strong. 0.3 or higher, but less than 0.7 is moderate, and anything less than 0.3 is weak, just so we have something as a cutoff spot. But different books, different statisticians are going to set those marks at different places, which one's stronger or not. So we can see a -0.7, that's a negative relationship. That would also, under my ruling here, I would say that's a strong negative. So this is a strong positive correlation, linear correlation. This is a strong negative linear correlation. And this is a moderate positive linear correlation. This is a moderate negative. And again, you could look at that and say, that doesn't seem moderate, it seems low. And again, we can disagree. I'm just using that as a cutoff. So we're going to be calculating these R values, but first we're going to just do some analysis. So the closer you are to 1, the closer this correlation coefficient is to 1, the more closely it corresponds to a linear model with a positive slope. The closer you are to -1, the correlation coefficient is more closely the data corresponds to a linear model with a negative slope. So this R value, generally speaking, it's how strong you are to align. Your data is to align. It is not the slope of the line. So while a positive R value corresponds with a positive slope, that's not the slope of the line. Same thing with a negative R value and the negative slope. You could have, a negative slope, very steep negative line, and that data could have, almost be -1, but a slope of -1 would be, just like at a 45-degree angle. So this is not the slope of the line, but it indicates whether it's a positive slope or a negative slope and whether it fits a line very well or not. And the closer you are to 0, the correlation coefficient is, the less the data set corresponds to a linear model of any kind. So you think about that parabolic shape, that would not, it would just be probably basically a slope of 0 going through that, or not slope of 0. See, now I'm messing it up. And R value is 0. R value is 0. Okay, so let's say we had this. We're going to look at number 16 on page 544, and they gave us this data set. Now their data set in the book is going to go horizontal because it fits the book better, but I'd rather look at these vertically. And we're going to plot these points. So these are basically XY pairs, right? So we're going to have to scale this. So when you're scaling it, you might want to look to see what's the smallest value. So it looks like 2.6 is going to be the minimum value, and probably 4.5 is a maximum. So those are going to be our x's. Those are our x-axis, right? So let's see. I just want to scale this. How many lines we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. Say 8, right? So that's about 2 units bigger. 8. We'll go up by quarters. How about that? We'll say we'll zigzag a little line here. We'll start at 2.5, 2.75, 3, 3.25, 3.5, 3.75, 4, 4.25, 4.5. Okay, so we'll scale that direction, and then we'll just kind of do the same thing for this other side. So 3.9 looks like the min on this, and then the highest value looks like 11.2. So that's like 4 and 11. Those are different by 7. Let's do this. Let's go 3. I think we can count by ones. 4, 5, 6, 7, 8, 9. Oop, nope, I messed up. Oh well, we'll go a little bit off the top of the graph. That's all right. And so I'll do a little zigzag to say, it doesn't go to 0. We're not starting at, this bottom quarter isn't to scale, is basically what that's saying. All right. 2.9 is just a little short of 3 and 5. So we're going to put a dot there. 4.2. So, I don't know, somewhere around there. 4.2 and 10. 4.2 and 10. So somewhere around there. 3.3, a little bit bigger than 0.25. And 11.2. So that's the one that's off the chart here. Okay. 4.5. 4.5, we got that. That's on this end. We go to 10. All right. All right, 2.6. So somewhere around there, just short of 8. Somewhere around there. 3.2. 3.2 is around there, just short of 4 at 3.9. 3.4. 3.4 is somewhere around there. 5.5. Okay, so that's what they want us to do for A. A is, the directions for A were make a scatter diagram and draw a line that you think best fits the data. So when you're drawing the best fit line is what this is called. You want about half the data above, half the data below. So maybe something like that. That might be a best fit line. But I think for that data, I'm trying to get some of the data above, some of the data below. It might be it should be a little bit steeper. I don't know. Just do your best. Try to get in the middle somewhere. Okay. So B, would you say the correlation is low, moderate, or strong, positive, or negative? Well, clearly it's positive. It's a positive relationship. I think that's what it looks like to me, at least. I guess somebody could make an argument that it would be negative, but it looks positive to me. It looks like it's generally trending upwards as we move to the right. Now, the strength of it, we got some of these are kind of way off of there. So I think I'm going to say, I'll say moderate. I'll say moderate. Low end moderate, maybe low moderate, low moderate, kind of the low end of the moderate scale, I would say. All right. So that's what they're going to ask you to do on a couple problems. You're going to plot them, draw a best fit line through them. Hopefully your data fits a line better than this one does. But then try to figure out what kind of relationship, positive or negative, how strong you think that relationship is. Don't worry, we're going to do a calculation and figure out a value for that R value to make that decision. But you're just going to make a guess at this point. You're just like, what do I think? How do I feel about that? All right, so let you do problems 1 through 11 odd, 13 A and B, just like I did this one, 15 A and B, just like I did this one, and 17 A and B, just like I did this one. And then come back and we'll talk about how to calculate the R value. Okay, so we're going to calculate the R value. So calculating the R value for the sample correlation coefficient involves this formula. So it's a little fun. All right, so let's look at what the different things are in this. N is the sample size, right? So you have, let me label these. So this is the sample size. And you can see there's another N here and another N here. All right. Sigma XY tells you this is the sum of the products of X and Y. Products of the pairs, right? So your X values and your Y values, real quick, let me go back here. Your X values and your Y values are in pairs, 2.9 and 5.0, 4.2 and 10.0. So this is saying multiply 2.9 times 5.0, do all that for each pair, and then add that total up. So that's what that sigma XY is. You're going to add up all the multiplying. This is the sum, again, this is the sum of X values, right? So you're going to add up all the X values. This is the sum of Y values. And you'll see, here's again, the sum of X values, and on this part, you're going to square it. And here's the sum of Y values. On that part, you're going to square it. And then on the bottom, we also have this part. And this is the sum of X's squared. I shouldn't say it that way. The sum of the squares of the X's. That's how I want to say it. Sum of the squares of the X's. Okay. And the same thing here. This is the sum of the squares of the Y's. So you're gonna square all your X's, add all that up. You're gonna square all your Y's and add all that up. You should calculate all of those first and then try to do this formula. Now, yes, there are programs that will do this for you. I will tell you on the final, you're gonna need to tell me what is the sum of X, what's the sum of Y, what's the sum of X squared, what's the sum of Y squared, what's the sum of XY, what's N, all that stuff. You're gonna have to tell me each of those values. So you need to make sure you know how to calculate each one of those values. Because if you use a program and it just tells you what R is, but it doesn't tell you what each of these values are, you're not going to get that part of the final correct. So make sure you can calculate each one of these individually. Make sure you can sum up the X's. Make sure you can sum up the Y's. Make sure you can square all the X's and then add them up. Make sure you can square all the Y's and add them up. Make sure you can multiply X times Y and then add all those products up. So make sure you can do that. But yes, as you get past this part, you can also use computer programs to do those calculations as well. All right, so here we go. You notice I made a nice little table here. I got my x values, and I have room for my x squared. I got my y values. I got room for y squared, and then at the end I got x, y, and then at the bottom I have the total, or I should say sum, right? The sigmas. So let me just kind of go through here. We'll just kind of work it out. And yeah, this is going to be a lot of number crunching, but that will help. That will help us get good at this. So 8.41, 4.2 squared, 17.64, 3.3 squared, 10.89, 4.5 squared, 20.25, 2.6 squared. And let me just warn you, I might make a typo. You know, if that's so, just kind of go with the flow, but you know, mentally say, okay, he did that wrong. There should be this number. And so our value might be different, but you know, I'm doing this live, so recording this live. So if I make a mistake, just, you know, be forgiving. This is what I'm saying. All right. So then what? 5 squared is 25. 10 squared is 100. 11.2 squared, I have no idea. That is 125.44. Sounds right. 100, 7.9 squared, less than 64 slightly, probably. 62.41, that's right. 3.9 squared should be less than 16 slightly. So yeah, 15.21 and 5.5 squared. Yeah, 30.25. And then x times y. So I'm going to multiply this column times this column, just going across. So 2.9 times 5, 14.5. 4.2 times 10, that'll be 42. 3.3 times, oops, back it up, 11.2. Looks like 36.96. 4.5 times 10, that's 45. 2.6 times 7.9. 20.54. 3.2 times 3.9. 12.48. 3.4 times 5.5. 18.7. Okay. So yeah, that's got to be somewhere between, you know, 15 and 24, you know, 3 times 5 and round those up to 4 and 6, you know. So all right, that looks okay, I believe. Let me just real quick kind of go through this. I'm not seeing anything jump out at me. 3.3 times 11.2, 36. Okay, so it looks all right. All right, so now what we're going to do is we're going to add up these columns, and these are the numbers we need. So 2.9 plus 4.2 plus 3.3 plus 4.5 plus 2.6 plus 3.2 plus 3.4. So, you know, this is easily something you could have like something like Excel calculate for you, and that would still be very close to, you know, basically doing it all by hand. Plus 6.76 plus 10.24 plus. Okay. So looking like 85.75 if you add up that column. 5 plus 10 plus 11.2 plus 10 plus 7.9 plus 3.9 plus 5.5. Okay, so it looks like that column adds up to be 53.5. Add up that column, 25 plus 100 plus 5.44. Looks like 458.31. And the last column, almost there. Almost ready to start doing crazy calculation. Plus 45. Okay, and I got 190.18. Hopefully I didn't make too many mistakes in that. All of that. So let me double check what I had calculated in the past. 24.1, 85.75, 53.5, 458.31, 190.18. All right, yay, first try. All right, so I guess second try, but the other one was a year ago, so I don't really count that. So now let me just go ahead and record all those values. Oh, I forgot. How many numbers do we have? So 1, 2, 3, 4, 5, 6, 7. We got 7. So our sample size is 7. Our sum of x, we said, was 24.1. Our sum of our x squareds was 85.75. Our sum of our y's was 53.5. Our sum of our y squareds was 458.31. And our sum of our x times y's are 190.18. All right, so we're going to use our formula. So I'm just going to put this in our formula. So now the way I write it isn't going to be 100% how I'm going to do it on the calculator, because I'm going to use parentheses when I write it, but I'm not going to use as many parentheses when I put it in the calculator, and you'll see. So 7 times the sum of xy, so 7 times 190.18 minus the sum of x, so 24.1, times the sum of y, which was 53.5. So that's going to be our numerator. And then we're going to do the square root times the square root, okay? And so our first square root, again, sample size is 7. Sum of our x squareds, 85.75, minus our sum of x's, that's the 24.1, squared. Okay, and then we're going to do the same thing with the y's. We're going to say sample size times the sum of our y's squared, 458.31, minus our sum of y's, that's the 53.5, 3.5 squared. And now we're going to type that in our calculator. So I'm going to get out of, oh yes, keep that please. I'm going to get out of there. I'm going to get in my calculator. So hopefully I can, here, let me see if I can make this a little bit smaller, just so I don't lose the thing there. Okay, so let's turn this on, clear it out. All right, so this is how I'm going to do it. I'm going to put the whole top in a parenthesis. Put the whole, let me get this. Let me get blue. All right, so I'm going to put the whole top in a parenthesis. I'm going to put the whole bottom in one parenthesis, one big parenthesis. So I'm not going to put these in there. And I'm not going to put a lot of these other little parentheses in there. I'm just going to say multiply. So this is how I'm going to type it in. I'm going to say parentheses 7 times 190.18. I could, but it's just going to be so many parentheses that it's going to get confusing. So if it's all you're doing is multiplying, you might as well just say times. But I don't like to say times when I'm writing it down on the paper, because you're like, is that a decimal? What is that? It's sometimes hard to read if you write it that way. So on the paper, I find parentheses are better, but I'm going to just type it in the calculator. I just say times. So close it up. That's the entire top in a parenthesis. Divided by parenthesis square root. So I get to the square root, I do second squared. There's my square root. Now this calculator starts me with a parenthesis. Some calculators will actually put you under the square root, but whatever. I'm going to type this first square root. 7 times 85.75 minus 24.1 squared. I'm going to close the square root, or if you're on a calculator, you can get out from underneath the square root. But I still want to, notice this, I'm closing here, that's the square root. I still have this parenthesis still on the bottom. So I'm going to say times, and I'm going to start another square root. And I'm going to do the other part. 7 times 45.31 minus 53.5 squared. And I'm going to close the square root, and I'm going to close the new denominator. So you can see why, like, you get so many parentheses, it gets confusing. So what you're doing. Now this value, if I do not get something between -1 and +1, I know I did this wrong. I know I made a mistake in how I typed it in the calculator. So let's see what we get. 0.511, 0.511. All right, so I got an R value. Got an R value of approximately, I think this section, they like to round these R values to 3 decimal places. So what is that? That's moderate. And that's what I said when I did the graph, right? I said it was probably moderate, kind of low, but moderate, maybe moderate. So it's moderate level there. So, you know, it makes me feel a little bit better about that guess of moderate. Now in the future, we'll talk about how to find that equation, that line. But at this stage, we're just trying to see how closely it fits a line, how closely it fits. So that's how you calculate the R value, and you'll do that for the 3 problems you did, the A and B. Now you're going to go back and do 15C, 13C, 15C, and 17C. So we're going to, you're going to look at scatter plotting and regression, figuring out how close that fits the line, and then in the future we'll do a regression. All right, so that's the end of this video.